Hello again. In this video, we are going to look at a particular example from the Introduction to Linear Transformations called the shear transformation. Let's start with this example. So let's let T go from R2 to R2 to be defined by our standard matrix multiplication transformation, T of x equals AX, where A is 1, 1, 0, 1. What does T project? So let's let x be in R2 in the domain, where x is going to be a two-dimensional x1, x2, some x1, x2. And let's look at T of x, which equals AX. So I put an A in x, and what do I get here? So multiplying these two matrices, we get the first row with this column is going to be x1 plus x2, and the second row is going to be it will be 0x1, so it's just going to be x2. This is a little more difficult than the ones I did on the last video. So what I'm going to do is I'm going to try to graph this. And how I'm going to graph this is I'm just going to pick some different points. So I'm going to pick the point 0, 0. So what does that mean? That means x1 is 0 and y1 is 0. And if I look here and plug that in, I would get the point 0, 0. Versus if I picked 1, 0, 1, 0, that means x1 is 0 and x2 is 0. So here I would get the point x1 would be 1, and then x2 would be 0, so I'd get the point 1, comma 0 again. Again, really what I'm doing here is taking T of 1, 0, which is 1 plus 0, 0, which is 1, 0. Looking at those 2 points, so I have 0, 0 here. That's going to 0, 0. And 1, let's make this a 1. That point is going to the same point there. Okay? So now let me try 0, 1. 0, 1, that means the x2 is 1. That goes to something totally different. So that means you would add these up. That would be 1, comma 1. So again, plugging in 0, 1 here, that would be x1 plus x2 is 1, but then this would be a 1 as well. So we have 0, 1, make that a 1 right there, is now 1, 1. Finally, I'm going to choose the point 1, 1. So I'm kind of thinking of making this little box right here is where I'm going for. And 1, 1, lastly, you would add those two, so you get the point 2, comma 1. So that point right there would transform to maybe this point right there, and let's extend that. And you would end up with what they call, right, a shear transformation. So you have a box that changes into a parallelogram. Again, on this one, just to make sure you see that, T of 1, 1 is 1 plus 1, 1. So x1 here is 1 and x2 is 1. So that's how I end up with a point 2, 1. Okay. So T is called a shear transformation. Let's look at the example in the book. If you look at example 3 in the book, their shear transformation is 1301. That also produces a shear transformation, as you can see here on the left. That's what it's doing, a sheared sheet going to the right. They define T to be R2 to R2 as such. And it says here on the second line, it can be shown that if T acts on each point in the 2x2 square shown in the figure, then the set of images forms the shaded parallelogram. So right here, down here, the key idea is to show that T maps line segments, these line segments, onto line segments, and then check the corners of the square map onto the vertices of the parallelogram. For instance, the image 0, 2, so they did the same thing I did, the image 0, 2, so they look at the a times x here, and they get 6, 2. 0 times 1 plus 3 times 2 is 6, and then here 0 times 0 plus 1 times 2 is 2. And the image 2, 2 is going to be 8, 2. Let's check that. So this row times the 2, 2 would be the first entry, so that would be 2 plus 6. And then the next one would be 0, 2. And you could have done this like I did for an x1, x2, looking at T of x equals ax. You can put in an x1, x2 by multiplying the matrix times our x1, x2, and what we would get is the first row times the column would be x1 plus 3x2, and then the last one would just be x2. So then if you would plug in your 0, 2 here, we get it automatically. The x2 would be, or the x1 would be 0, and the x2 would be 2, so there's where the 6 would come from, and then this would be the 2. And then the 2, 2 would plug in 2's everywhere, so that's where the 8 would come from, and that's where the 2. So if you look down at 0, 2, it now becomes 6, 2, 0, 2 becomes 6, 2, and the point 2, 2 becomes the point 8, 2. 0, 0 stays the same. And the point 2, 0, x2 would be 2, would stay the same as well. So the top is shifting, but not the bottom. In general, any matrix in the form 0k, 0, 1 is a shear transformation. That k there is going to make it a shear transformation. So if you look in the book, in the next section, there's a table that has all the different transformations, and table 3 is the shears. And you can see here we did actually a horizontal shear. But there's actually a vertical shear if you put K in this bottom left corner instead of the top right corner. Hope that helps.